Density is also a property that makes water unique, and we'll talk about why that is in a little bit, but let's first talk about what density is. So density is a measurement of how tightly packed different molecules in a substance are. It depends on the mass of that substance and the volume. And so our units are either grams per milliliter or grams per cubic centimeter, depending on what type of substance we're measuring. So liquids are typically measured in milliliters, solids are typically in cubic centimeters. So the more tightly packed our molecules are, the higher its density. The less tightly packed the molecules are, the lower its density. So think about what that means for different phases. So which is going to be more dense, a solid or a gas? Well, a solid, because the molecules are more closely packed. Here is a column of different liquids that are all stacked on top of each other based on their density. And there's also some objects that are in this column, and you can roughly tell what their density is based on the layer that they're floating in. So the least dense liquid, the lamp oil, is at the top. The most dense is at the bottom, which is the honey. So which state of matter do we think is going to be the most dense? Well, solids typically are the most dense because the molecules are most closely packed. Liquids are a little less dense, and gases are significantly less dense than the solid. How about water? Okay, so we're pretty familiar with water, where we have liquid water on the bottom of our glass and we have ice on the top of our glass. So what does that tell us about the density? Well, it means that the ice is less dense, but it is a solid. Well, ice is unique in the fact that its solid is less dense than the liquid. Although it's what we most commonly see, this is a very unique property. Most other substances, the solid will sink in the liquid. And this makes water unique because its solid floats when most other substances, the solid would sink. So why is that? Why does ice float? Well, ice floats because when it forms the solid, it actually becomes less dense because of the arrangement of the molecules. And the reason for this is because of hydrogen bonding. So the hydrogen bonding actually spreads the molecules out just a little bit, making the volume larger than what it would be in the liquid. And so makes our ice less dense because of our hydrogen bonding. So think about what effect this has. What if ice sunk? How would this affect aquatic life? Well, if ice sunk when it froze, the lakes would freeze at the top and it would sink to the bottom, and there wouldn't be any ability for there to be life. All the fish would be frozen into a solid block of ice. And so because water is unique and the ice floats, it allows the aquatic life to live underneath the ice. Water also has a very high surface tension. So surface tension is the resistance of an external force on the surface. And you may have seen this if you see bugs skittering across the top of water, or if you very carefully floated a paper clip, you can actually get a paper clip to float on the surface of water, and that's due to surface tension. If we don't have gravity, it becomes even more apparent. The water will actually form spheres in space due to surface tension. They want to minimize the amount of molecules on the surface, and the water will actually collect around that surface and won't drip off. Capillary action is also unique to water, and capillary action is when the liquid will climb up a thin tube against the force of gravity. And so this happens because of what we call adhesive forces. The water is attracted to the glass or to the sides of the tube, and because water is attracted to itself, it pulls the other water molecules up the tube. The narrower the tube, the further the water climbs up. If we have other substances like mercury, mercury is not attracted to the glass, and so it does not climb up into the glass tubes. So it has an opposing trend where the thinner the tube gets, the less the mercury climbs into the tube. You maybe have done an experiment if you've ever used Queen Anne's lace or celery or carnations as well. You can see capillary action happening if you put it into water with food coloring. It will actually draw the liquid up the capillaries inside the plants and color the leaves of the plant. This is what leads to the meniscus. So the surface tension and the attraction for the water to the glass leads to the water creeping up the sides just a little bit. And that's what forms the meniscus when we pour it into a graduated cylinder or a test tube or a burette or any of the reading instruments that we use to read volume. And this is why we standardize the measurements where we're reading at the bottom of our meniscus. If you notice, because mercury is not attracted to the glass, it actually has the reverse. It'll bubble up in the middle because it's more attracted to itself than it is to the glass. Water is also unique in the fact that it has a very high specific heat. Specific heat is the amount of energy that you need to add to change a certain amount of the substance by 1 degree Celsius. And so water has a very high specific heat of about 4.184 joules per gram degree Celsius. Our metals have much lower specific heats, so they are all less than 1. This is part of the reason why we use them to help in make pots and cook out of. They gain heat quickly to heat up our food. They also lose heat quickly. The reason that water has such a high specific heat is because of hydrogen bonding, because it takes more energy to overcome those intermolecular forces. So we have to add more energy into the substance because our intermolecular forces are stronger. It takes more energy to get those molecules vibrating and to leave the surface of the liquid, or to change the temperature of the liquid. Once we overcome those intermolecular forces, the molecules can start moving faster, and we can change it from a liquid into a gas. And those substance temperature eventually begins to rise. This is also why when you're walking on the beach, the sand is much hotter than the water. So we're still gaining the same amount of energy from the sun. Same sunlight is beating down both on the beach and the water. But because the sand does not have hydrogen bonding, it can absorb the heat energy faster than the water. And so its temperature is higher than the water that is right next to it on the beach. On the beach, the sand is not soluble in the water. So what does that mean? If it's insoluble, it means it does not mix. It won't dissolve. However, the salt that is in the ocean, that is soluble. And so the two substances are soluble. They form a homogeneous solution where everything mixes together. If we have an insoluble liquid will actually sit on top of the other liquid. It is a heterogeneous solution. It forms layers. We can also have exothermic and endothermic reactions. So exothermic is when energy is released by a reaction. Many of these reactions happen in water. So when energy is released, that increases the temperature of the surroundings or the things around it. And so exothermic reactions give off heat. Endothermic reactions will actually absorb heat from the surroundings, and so it'll actually cool down the surroundings. So if you've ever used a chemical cold pack, that's made out of ammonium nitrate typically, and so when ammonium nitrate dissolves in water, it becomes endothermic. It absorbs heat and it cools down any injury or burn that you have. Exothermic reactions like chemical hand warmers, those tend to be the oxygen reacting with iron, and oxygen reacting with iron gives off heat, and so that raises the temperature of the surroundings around it.